All right, so let me see if I can explain this. All right, so 31. So this is the bowling ball problem. So it says a bowler throws a bowling ball with a radius of 11 centimeters. So let's go ahead and write all this stuff down. Radius is 0.11 meters along the lane. The ball in the figure slides on the lane with an initial speed, v, center of mass, and then the little o just means initial. I'm going to use I just because I like initial and final better than not. All right. And an angular speed initially of 0. So does this make sense to you guys that when you throw a bowling ball, the velocity that you give it is equal to the velocity your hand is moving when you let go, right? Yeah. Okay? And then, it accelerates a little bit as it falls, but whatever, right? And when you let go of it, you're not necessarily... basically what they're getting at is this, that when it first hits the lane, all of its motion is translational because you sort of haven't given it any spin, right? So what's going to happen is for a little bit, it's going to slide, right? You see what I'm saying? So is it going to slide forever? What's trying to prevent it from sliding? Friction, right? So at what point on the ball does the force of friction act? Down here, right? Okay? So I'm going to move this arrow here. Oh, no, I'm not. Oh, darn it. I'm going to erase this arrow because I think that it is misleading. It looks like a force. I'm going to label this with a V and label this with the force of friction. All right, so do you guys agree that that's really the only force that's going to affect its motion? Obviously there's gravity and a normal force, right? But those are going to cancel out. So really all we care about here is friction, right? So how is this force of friction going to affect the linear velocity? In other words, the velocity of the center of mass. What's going to happen to the velocity of the center of mass due to the force of friction, you guys? Don't overthink it. If you've got a thing sliding to the right and friction's pushing to the right, what's going to happen? It's going to slow down, right? Okay? Everybody okay with that? It's sliding, friction doesn't want it to, friction's going to slow it down in an attempt to make it not slide. Good? All right. Additionally, our angular velocity is 0. But remember, our center of mass is here, so we're producing a torque around this pivot point. And as a result, it's going to begin accelerating angularly. Good? And eventually, we will achieve a point at which the velocity is equal to the angular velocity times the radius. And it is at that point that the smooth rolling begins. So, does everybody understand what I mean when I say smooth rolling? It's rolling but not slipping at all. Clear? Anthony?
So smooth rolling, you just ignore friction because it's like pivoting, right? Kind of?
You can think about it that way.
Okay. But when it's slipping, you still have to include it because part of it is like sliding.
Correct.
Okay.
Yes. Gosh, I'm hesitant to agree with ignoring friction.
Well,
because the friction is responsible for it rolling.
Yeah.
Do you know what I mean?
Yeah, but it's not slowing it down.
Well, it is because it's converting rotational kinetic energy. I'm sorry, it's converting linear kinetic energy to rotational kinetic energy. Let me see. I guess you're right. If it's on a horizontal surface, friction is not going to do any work. Once it's smooth rolling, friction will not be doing any work, so it won't slow down. I agree with that.
Okay.
I agree with that. Does that make sense, you guys? All right, so this idea here is at the crux of this problem. What we want to do is we want to figure out at what point it is that the velocity of the center of mass is equal to the angular velocity times the radius. And it's at that point that, the velocity of a point on the outside matches the velocity of the motion, and it stops slipping and just begins rolling. Follow? Okay, so that is a big, big idea. All right, so let's see. What does it tell us? It tells us the coefficient of kinetic friction. Ew, who wrote this problem? Coefficient of kinetic friction is 0.21. The kinetic frictional force, Fk, acting on the ball causes a linear acceleration of the ball while producing a torque. This is what we just talked about. That causes an angular acceleration of the ball. When speed v v center of mass, has decreased enough and angular speed omega has increased enough, the ball stops sliding and then rolls smoothly. So A says, what then is v center of mass in terms of omega? So I think that's what they're looking for there for part A. So, is everybody cool with that? Is that all they want for part A? I don't even remember. Oh, stupid sharpener. Wait a minute, what's going... Oh, I'm looking at the wrong answer. Oh, that's right. The only answer I put on here was the last answer. Okay, I gotcha. All right. Okay, so yeah, the only answer I put on here was F. So we got to kind of work our way through it. So, for part A, I think this is all they were looking for, is for you to make that realization. So are we good with that? Does that make sense? All right, part B. During the sliding, what is the linear acceleration? All right, well, I guess I should finish my free body diagram up. So we've got our force of kinetic friction. Let me move. Oh, man. Stupid smartboard. Doing exactly what it's programmed to do. Okay, so let's finish our free body diagram here. We've got our force of gravity is going to be mg. Our normal force is going to be big enough to cancel that, so it's also mg. And our force of friction then is going to be 0.21 times mg, right? Normal force times coefficient. Everybody good? All right, so part B wants to know the linear acceleration. So what does the linear acceleration depend on, you guys? Think back to 12 chapters ago. Well, not 12 chapters ago. 7 chapters ago. 8 chapters ago. Somebody said it. Force. It depends on the net force, right? So the translational acceleration is net force over mass. So my net force is just the force of friction, right? So that's 0.21 mg over m. The m's cancel out, and you get 0.21 g with one tiny little mistake that I overlooked. Negative acceleration. Remember, g is understood to be positive 9.8. Our acceleration is negative style. All right? Cool? All right. Part C says, during the sliding, what is the ball's angular acceleration? So in the same way that linear acceleration depends on force, angular acceleration depends on torque. Okay, so... Say that again? Oh, good. Can we do the jumper thing here?
No.
No. Can you tell why, Adam?
Because it's sliding, it's not.
Good. Yeah, there's not necessarily a connection between the linear motion and the angular motion yet, because it's sliding. Does that make sense?
Yeah.
Everybody? That's important. I'm glad you asked that question, because I didn't want to overlook that. All right, so that means our alpha is our net torque over our rotational inertia. So how am I going to find my net torque, you guys? What force is providing the torque? Friction, right? What is the length of my lever arm? The radius of the ball, right? Follow? Okay, so this is going to be our force of friction, which is 0.21 mg. That's my force of friction, times the radius of the ball, which is 0.11, right? Being sloppy about units. Everybody cool? Hey. All right. Let's see. That was my Fonzie joke for the day. Check that off. All right. Now we got to find our rotational inertia. Talk to me about the rotational inertia of the bowling ball, you guys. It's a solid sphere. So 2/5 mr squared. 2/5 m times 0.11 squared, right? I am happy right now. Why am I happy? And then I'll answer Tyler's question. The m's cancel out. Kabam, kabam. And yeah, one of the 0.11's cancel. Sure, yeah. So you can do this and this if you want. Question?
Johnny, give me my calculator.
So there's a difference between the acceleration and the force. Follow? Everybody good? All right, so let's see what this gives us. 0.21 times 9.8 times 0.11 divided by 0.4 divided by point... Oh, my 1's canceled. Darn it. Curse my feeble brain. So you got 46.77 radians per second squared. Don't use R for radians. All right, so is everybody good with C?
Wait, isn't it negative? Or no?
Cool, so let's talk about our signs here. Linearly, are we gaining or losing velocity? Losing. Angularly, are we gaining or losing velocity? Gaining, right? So, and we want to find the point at which they sort of meet, right? Not really, because one's angular, one's linear, but where they sort of match up to be friends, so they can like shake hands, right? Because that's what friends do. Unless they're germaphobes, in which case they don't. Okay, so D, how long does the ball slide? E, how far does the ball slide? F, what is the speed of the ball when smooth rolling begins? So thoughts about where to go from here? I'll be honest with you, I haven't looked at this problem since I signed it last year. I remembered that I like this problem. I'm a little puzzled by D and E. I feel like we should be able to find F before we get D and E. But maybe I'm wrong. Patrick, what do you got?
I have a thought.
You have a thought?
Yeah, wait, what would have those?
D is,
The time, right?
no. Oh yeah, how long does the ball slide? Yes.
Okay, yeah, so we have the angular acceleration and the radial acceleration. So, let's see what I did. Okay, I haven't really looked at this in a while either. So I did like, the initial angular acceleration is 0, and I did plus the acceleration of the angular times time, and I multiplied by the radius. To get
Say that one more time here. Let's see. Hang on. I think you're good. So part D. Say it one more time.
In parentheses, I put 0 plus 46.8t.
Okay, so you're doing this. Omega F equals omega I plus alpha t.
Yes.
Your initial angular, so you're saying, all right, well, my initial angular velocity is 0. I love where this is going. This is perfect. Plus, he's saying we just found our alpha, 46.77 radians per second squared times t. Love it.
And then I put that in like that thing right there in parentheses, and I multiplied by 0.11, which is the radius.
Okay, let me come back to that. Yes, I'm going to do what you're doing, but you're doing a lot in your head there, and I want to make sure everybody's on board with what you did. So does everybody agree with this? That right there is an expression for our angular velocity in terms of time, yes? All right, what other type of motion are we concerned about? The linear. So let's come up with a similar equation for our linear motion. So if I do that, the corresponding equation would be this. Yes?
Yeah.
So let's plug in our numbers for that. What's our VI, you guys? 8.5 plus our acceleration is negative 0.21 g, which is some number which I haven't figured out yet, times t, right?
Yes.
So that's an equation for my VF. Good? All right. What should be true about the angular velocity at some instant and the linear velocity at some instant? Should equal this, right? Ah, very good. Thank you, Patrick. Oh, shoot, what did I just do? Oh, come on, you stupid smartboard. There we go. That's right, I'm sticking with it. All right, so VF equals omega F times R. So that means that, it means that 8.55, no, I added an extra 5 there. 8.5 minus 0.21 g equals, oh, I forgot my t, sorry. T equals 46.77 T times our radius, which is 0.11.
Wait a minute. Now I'm confused.
Where did I lose you?
This black part.
The black part? So all I did with the black part, shh, you guys. All I did with the black part is I said, all right, I know that at the instant when the smooth rolling begins, that this first black statement has to be true. Are you good with that?
Yes.
Is it-
Is the initial W is 0?
Yes.
All right, I understand.
You good?
Yeah.
Because of that, right?
Yeah.
So then all I did is I plugged in these two yellow values, the two yellow equations here, over here, times R, and the R is 0.11, right? Follow? Patrick, is this basically what you did?
Yeah.
Cool. Everybody good?
Yes.
All right, so solve this thing, yes? So what does the time turn out to, Patrick?
1.18 seconds.
1.18 seconds. Awesome. Everybody cool with that?
Yeah.
All right, so now, E says how far does the ball slide? So what am I looking for? Delta x, right? So for delta x, it's just 1/2 a t squared plus VIT. Plug in your numbers. Did you plug in the 9.8 for G? Is the 1 point, anybody else get 1.18? Should we check it? Let's run through the math and make sure that's right. All right, so let's see. If we simplify this top thing up here, donde es Spanish? That I don't speak. All right, let's see. So 8.5, why am I writing that again? So this is 8.5 minus, let's see, 0.21 times 9.8 is 2.058. T equals 46.77 times 0.11 is 5.1447 T. Sorry? So add, yeah, this should work. Gotcha. Positive because we're gaining angular speed. All right, so everybody's good now with the time? All right. And then whatever, part E we talked about, right? 1/2 AT squared. And then finally, what's the last question? What is the speed of the ball when the smooth rolling begins? So now you just take your time and plug it in to the VF equation, right? And that'll give you your final velocity. Questions, you guys? There's a lot going on there. Did I lose anybody? Okay, cool. Right on. Good job. That's a neat problem.